So I'm going to begin here to show you that I've got in this example, I've got on the left-hand side a master microcontroller, which I will be used to demonstrate SPI. And I've also got on the right-hand side a slave, also a microcontroller, but in this case a slave, also to communicate from the left to the right, master to slave, and slave back to master on a request, and making use of SPI. I've also connected here an LCD display to the master and also to the slave, just to show us a little bit more in detail of what's happening with this device. So I've got two programs, and of course this is the ATMEGA328P, both of them. I've got two programs here, one for the master and one for the slave. Let's go to the master first of all, and then I'll go back to the slave. Maybe I must just give some credit to a company by the name, or a site by the name of Electronic Wings, EW. I actually used the program that they've got there, which was written for an AVR 16 or 32 bits, and I've adjusted that slightly to accommodate my program in this specific case. So I think what I'm first of all going to do is just to show you the master program. So I'm just going to quickly step through it so that you can, if you need my program. So this is the program that I use to display detail on the LCD display. Let me just quickly step through this. Then you've got the whole of the program, and you can actually copy it in some way or maybe retype it. So this is what it looks like with all the different functions in there. And if I can go, let me just, in this case, I'm just going on the master, I'm going to scroll up. I will be working from the main. And on the slave device, I also just want to quickly scroll down and basically capture everything so that you could also copy this program if you want to make use of it. So if you look at the line numbers, you'll get a nice picture of what I have done here. So in this case, let me also go back to the main function, and let me begin by explaining this program now. So yes, for the LCD, I have initialized it. You can go back and look at I've already explained this in previous videos, but go and look at the LCD initialize. And then I've got here an SPI initialize. And if you look at the SPI initialize, basically this is the routine here. And the master out, slave in, and this clock line, and also the enable line, they were actually made outputs, pins on the master, of course. And the master in, slave out is made an input pin. Then also what's happening here is the SS pin, or the enable pin, is made high at this stage. Then if we look here in the control register, as you can see there, the SPI is enabled, made 1 in other words. This is a master device, so I made this 1. And with this SPR0, together with this specific bit here sitting in the status register, that determines that the frequency is going to be the oscillator frequency, and in my case it's 16 megahertz divided by 16. So the oscillating frequency, or the crystal, the bit rate frequency will be 1 megahertz, which is quite fast. So this is where the speed is actually then set by the initialization. If we can go further now, this functions here is just, in my case, 1 means the X value, means it's actually the first character, and 1 on the top line, write down master there, and then on the bottom line, this is actually on the bottom line, writing down TX, and this is just on the right hand side of TX. This is, at some point we'll see when I test it, this is where the value that will be transmitted will be placed. RX, this is where the value that's been received from the slave will be placed. In this case, SS is made 0, which means the slave will be enabled at this stage. There's a register by the name of count, which is starting at 0. And let's see. So let's see what's happening with SPI write. And so the first count is 0. So the 0 will be placed in here, and this will now be written to the slave. But let's go to SPI write and see what's happening there. As you can see there, there's some char by the name of flush buffer. And what happens here is, okay, first of all, the data, that 0, which must now be written to the slave, is placed into the data register here, the specific one here. This says write the data to be transmitted. And then this specific line will go and check, monitor the status register. Because at this stage, when the data is being transmitted, this SPIF will be a 0. So it will actually sit in this line until all the bits that we received in data, in this as an argument here, whatever we receive here, that will basically, at the end of the day, as soon as it's transmitted, this flag will jump up to become a 1. Now, what is happening here is then after this, that SPDR, the data register, is just basically copied into the flush buffer. And the reason for that is the SPIF flag is cleared by first reading the SPSR, so that's the status register, and here it is read with SPIF set. So in other words, the moment that the data goes out, this will become a high and it will be read. It would have been read the whole time, but at that stage, the outcome, the specific bit would have been a 0, but at some point it's going to become a 1. And then if you're accessing the SPDR, like in this specific case, the SPDR is actually placed into the flush buffer. That is when this specific bit will be reset again. So I want you to take note of this specific method. Maybe I should just put this on the next line. Because here, this thing is read until it is a high, and then the data register is actually placed into this flush buffer, and this is how you reset this SPIF flag. So this is how the data will be written. So in this specific case, it's a 0, that the first one is a 0 that will be written to the slave device. So what I've done here further is just to say, let's go to the bottom line. It's actually to this position here. 1, 2, 3, 4, it's position number 4. This is the position there. And the 2 means it's the bottom line. And just go and write down count. So basically, although the SPI module, the master, has transmitted a specific value, in this case 0, it will just place a 0 there also just to show on the screen that a 0 was placed there. Count will be incremented to 1. There's a short delay there. But now I want to go over to the slave device, and I want to see, because the data has now been transmitted. So on the slave device, let's have a look at the slave device. What is happening there? If I go to my slave device, I will be sitting again in the slave. As a start, I've written at the top of the screen slave. RX is what the slave has received, and of course TX is what the slave will be transmitting. So in this specific case, I said RX count, it's a variable, is equal to SPI receive. So let's go to SPI receive. So, but we must remember now, the master has transmitted a 0, and that 0 came to the slave. So let's have a look at what's happening in the slave. If we look at this SPI receive, it will be SPI receive. It's this one here. In this specific unit, so when this unit starts up, it's actually going to sit in this line, and it is going to wait for SPIF to become high. And it will only become high if the data register is actually filled with something. So this is where it will sit, and as soon as all the data from the master is in, it will actually jump to this line. But if you really think about this, so it says here again, if you want to be clear that specific SPIF flag, you must read SPSR when this SPIF is a 1. as soon as you jump to this line, you are actually doing that. And when you read SPDR, the data register again, you are also making sure that the flag is then reset. But now SPDR has the value received from the master, which in this case was a 0. And if you look at the program, that 0 will now be sitting in RX count. And all I'm doing here is just to say that go to position number, go to position number 4, which is here, and show what has been received. So in RX, there will be a 0, just after RX, of course. And then what I'm doing is the following. I am saying go to this position, which is here. And now I'm saying, let's take that RX count and add 10 to it. So if the answer was, first of all, if we received a 0, I'm actually going to place a 10 there, which is 10 higher than what we received from the master. And then I say, go and write SPI write this specific same value, which is the 0 plus 10. This is just the first one. And if I go to SPI write in my program now, this is extremely important to realize this. So SPI write, again, this is the first. What we will do is we will place the data, which is in this case, well, the very first instance, it will actually be a value of 10. 0 plus 10 is 10. Will be placed in the data register. But what we're doing here is we are actually waiting for data to come from the master, because this flag will only jump up, if ever I talk about jump up, it means it goes high, it is set. This flag will only set if data has been received from the master. So this is, I really want you to see what is happening with this thing. So, but also, which is important for us to realize is this. Although I'm placing in the data register a value of 10, this flag cannot jump up if there's also no clock pulse. And if the master is not sending anything, there will be no clock pulse. So what we need to see here is the moment that the master sends something again. That is the moment that I can actually go to this next line here. So, but let's go back to we'll stop in the slave at this stage. Let's go to the master unit now. So we've already seen we are basically, a count is now a value of 1. There's a short delay, but then I say that slave val equals SPI read. So let's go to SPI read. And this is actually where the master now wants to read from the slave. So SPI read is this one here. And this is now very important. I've said previously on the slave side, we are actually stuck at this stage in this while one loop because there's no clock pulse. So if the clock pulse is only generated by the master. So if the master generates a clock pulse, only then at the same time can I send data. The slave can send data to the master. So let's look at this one here. So can you see that in this instance, it's actually a bunch of junk. It's whatever value, FF, it doesn't mean anything. If we load FF hex into the data register, the master will start to send data to the slave. But at the same time, that it also generates a clock pulse. And because it's generating a clock pulse, the slave can actually now send data, start by sending data to the other side, back to the master, in other words. So this will be sent, and as soon as, if I go to this one, as soon as that junk data is actually being received by this is now the slave. If that junk data was received by the slave, this flag will jump to be a 1. It will go up to be a 1, and I will get to this point. But at the main thing is, while this clock pulse was generated, my data, which was sitting in SPDR, was at the same time, it was also sent to the master. Here, I'm just reading whatever. In this case, it's going to be the junk that was sitting in this FF that I received. I'm just putting it in the flash buffer, and all of that is just to reset the specific flag here. So on the master side, if I go back to the master, remember my slave has send data to, when I was sending, or the master was sending this junk, the slave actually sent back a value of 10, 0 plus 10. And as soon as this, well, if at the moment that it's done by sending the data, it's just going to wait here. But as soon as the data has been sent to the slave, I will return what is now sitting in the master device, which was received from the slave unit, which is going to be a value of 10. And if I now go to my program, you will see I'm just saying go to position number 11, which is receive that position there, and it will display a value of 10. So that's where it's going to start. And then the whole process will be, because count is now a 1, so it's going to start sending a count of 1. The slave will send back a value of 1 plus 10, which is 11, etc. And this is basically the operation. Let's have a look at the Proteus file for this thing. Let me start this, and as you can see, it's 0 here, and it starts with 10, which was received back. So 0 to, if you look at what is transmitted from the master and look at what is received by the slave, you'll see if it's 6 or 7, it's 7 here, 8 here on the right-hand side, and if it's 9 or 10, with 10 added, this is what the slave is now sending back to that side. So you will see that there's sort of a difference between what you see here and what you see there of around about 10, with a slight time difference. And this is how you can actually generate your own programs using a microcontroller and two microcontrollers using SPI. So this specific program clearly shows us how can I send data from the master to the slave and from the slave back to the master. But as I've said, to me, one of the most important points where I actually myself took a while to figure this out was that even if you put this data into the data register, you will not transmit anything. It will wait till the slave comes back, when the master comes back to you and the master says, master is transmitting data. So we're waiting for this master to send back something. And in our case, that send back something was junk data, but the point was to get the moment that the master starts sending the data, there's a clock pulse, and then your data register can send the real data, as I've said in the beginning, of 10 maybe, can send it back. And this is just flushing it. But while the data has been sent back, the data was sent back to the master, and the master can receive that and display it in some way. I hope this made sense, but I think if you read through the instructions and if you read through all the comments that I've made in this program, it should be quite clear. Thank you.